Good morning, Internet. I am Matt Buyak, and this is the fourth and final video in my primes series. So this is the video where we really get to do the interesting stuff. In some ways, everything we've been doing for the last 3 videos has just been set up to get to this point. You'll recall in the first video, we built a library called libnumtheory to hold our code. In the second video, we created this primes class and added our code for calculating prime numbers. And in the third video, we wrote some tests to make sure that our code was behaving correctly. So in this video, we will finish our primes class by allowing it to calculate an arbitrary number of primes. You'll recall that we were limited by the size of our sieve. And so we'll need to find a way to allow our sieve and our primes array to expand arbitrarily. Now, in order to pick the right data structure, you'll notice that a static array is just not going to do the trick, it being a fixed size. And so we need to think about what data structure we can use instead. And to do that, we need to consider the usage pattern of our primes list here. So in particular, we know that our primes list is always going to grow in size. We're never going to remove elements. We're always going to add elements to the end, not in the middle or at the beginning. But we also need to be able to read elements from the middle of the list. And fortunately, there's already a data structure that exactly matches this usage pattern, and that is the vector. So this is from the standard template library. This website, cppreference.com, I would highly recommend as a reference for all things C++, just as a side note. But this is the data structure that we're going to use for our array of primes. So let's get into that. So the way we declare a vector is as follows. It's going to be std vector angle bracket uint32t angle bracket primes. So what is all of this? So this std : is just indicating the namespace. We haven't talked about namespaces yet, but it's just another way of organizing code. You've seen this : operator with our class before to indicate that something is part of our class. It can also be used as here to indicate that vector is part of the std namespace. And std is just the standard template library. Now, in order to use that, we will have to include a header file, vector. And then getting back to our declaration here, these angle brackets are just indicating that uint32t is the contained data type. So vector is a container class. It holds other objects or data types. And in this case, it's a vector of uint32t. Now, as I said, this will automatically expand as we add elements to the end. We can read elements from the middle. This is precisely what we need. There's also a member of primes that allows us to get the current size. And so we don't have to track that ourselves. We can get rid of this num primes. We don't have to have this prime size anymore to indicate the size of our primes list. We don't have to initialize num primes up here. And now going over to our implementation, let's just look for primes. So we don't need to, again, we don't have primes anymore. And so we'll say if primes.empty, again, this is another member of the vector class. You can find all of these again on the reference page here, yeah, you see here's that empty, there's size. Those are the methods that, that we're using. And so this just checks to see if primes is empty. And so we can say if primes is empty, calculate us some primes. And we'll do likewise here. Now down here, this is not. Excuse me, I missed one thing. So here, where we're reading from our primes array, you can see that when it was an array, we were using this square bracket operator to do so. And it turns out that that will still work with vector. Again, going to the reference page, you can see here this operator square bracket. So you can see that that is used to access specific elements of the vector, just like if it were an array. And so we can leave that code unchanged. Continuing down, this, however, is not how elements are inserted into a vector. We will have to change that to a slightly different syntax, like so. Again, we don't have to track the number of primes ourselves, and so that should be all the changes we have to make. So let's go over and rebuild our library. Oh, and I added my vector here without actually deleting the existing array. There we go. And I left a spurious colon here. All right, there we go. And we shouldn't need to actually rebuild our tests. I don't think. Oh, I guess we did. Okay. And let's run that. Success. All right. So we haven't broken anything yet. That's a good sign. So that was pretty straightforward. So you might think that it would be just as easy for our sieve. We just switch it over to using vector, and we're good to go. But there are a couple of wrinkles in that where the sieve doesn't match our primes, or doesn't match the vector behavior quite as well as our primes list did. And so we'll have to be a little bit more careful about it. Now, there is one way in which we do get some significant benefit from switching our sieve over to using a vector, and that is if we go again to the reference page, we'll see that vector has a specialization just for Boolean values. That is, it behaves slightly differently when it's containing a Boolean value. Although it's not required, what this usually means is that it stores one value per bit rather than one value per byte. You may recall that we're currently, our sieve is an array of Boolean values, and each of those bools is going to be at least 1 byte in size. But you really only need 1 bit in order to store a Boolean value. And so the vector of bools will take advantage of that and pack your values in to be much more space efficient. You're possibly 8 times as efficient in terms of space usage. So that is an immediate benefit of switching over to vector, even if we don't use the ability to expand. So we're actually going to do this in 2 steps. As I mentioned, the expansion behavior for our sieve is a little bit more tricky. And so first, we're going to switch it over to using a vector of bools, and then we will figure out how to make it expandable. So let's do that. If we do std vector bool sieve. Again, we don't need that. We will still need our sieve size for now because we're not yet going to make it grow automatically. And so when you first create the vector of bools here, it's going to have size 0, which is obviously not what we want. We want it to have size 250,000 or whatever we set our sieve size to. And the way we do that is through the constructor. So you'll recall our class here has a constructor. It's currently not doing anything. But these vectors also have a constructor. And the constructors for our vectors are going to be called just before the constructor for our primes class. And our constructor for our primes class doesn't take any arguments, but some constructors do. And in particular, if we go to the constructor for our vector here, and we take a look at the fourth possibility here, you can see this reference page can be a little bit intimidating with all the many different variations of the vector constructor. But this is the one that we're interested in, which allows you to create a vector with a specific number of elements in it. And the way that we do that is in our constructor here. You may remember me previously talking about the idea of an initializer list. And that's the mechanism that we'll use to call the constructor for our vector. So if we say sieve, sieve size, then this will be called just prior to our constructor. Now, you might be asking, so we're initializing our vector to have 250,000 elements in it to start. But what's in there? We haven't specified the values of those elements. Do they start at true, at false, or is it random? Well, it turns out that if you go back to the reference page here, you'll see that it mentions, going down to number 4 here, that the elements are default inserted instances of T. A little bit technical. You probably would have to dig into that a bit to actually understand it. But what it comes out to is that the elements that we're inserting have the value of false for Boolean values. Now, this is a little bit of a problem because if we go back to our code here, you'll recall that we're initializing our sieve to be all true values rather than all false values. And so that's the opposite of what we want. Fortunately, there's an easy way to get around that, and that is to switch what is actually being tracked by our sieve. So previously, we were tracking the prime numbers. That is, we would set everything to prime by default, and then we would go through and mark the multiples of other primes to remove the composite numbers. But instead, what we can do is we can initialize everything to 0. That is saying that none of the numbers are composite, and then we can go through and mark the composite numbers as true. Now, to make sure that we keep clear in our own minds that we've made this switch, we're going to rename our variable here to be composite. And we'll have to change that up here also. Okay, so now we're ready to go through and update our source code here. So we'll just search for sieve. Okay, so as I mentioned, we've renamed this. but also we flipped the meaning of the elements of our sieve here. And so we'll have to say if, return not composite. And now you can see the advantage of having renamed this. It makes the logic very clear. Okay, so we don't need to be doing memset. We will now be setting these to true instead of false. We've renamed this to composite. Here instead, we want to say composite.size. Here we'll say if not composite. Here we'll say composite.size. And here we'll say composite equals true. Okay, and let's retest everything to make sure we didn't make any mistakes. Okay, good. Still haven't made any test-breaking mistakes. So now we have switched our sieve over to using a vector of bools. Now we want to be able to expand it as needed. So as with our vector of primes, we could just add elements one at a time to the end of our sieve. But that would be pretty inefficient, and it's not really the usage pattern of our sieve. You'll recall that, for example, if we had generated the first or the primes less than 10,000, and then we wanted to instead generate the primes less than 20,000, we don't want to increase the size of our sieve by 1. We want to increase it by double. And so it doesn't really make sense to add one at a time. We want to be able to significantly expand the size of our sieve here. And so that's going to be our strategy, is that we specifically expand it rather than just adding elements one at a time. And the method that we'll want in order to do that is resize. So if we go back to the vector here and we look down the list, you see this method here, resize. That's going to be what we want to increase the size of our sieve. Okay, so we'll want some new code for handling that. There are a couple of cases where we'll want to expand potentially the size of our sieve. And so we'll want to have the same code called from both of those places. And so we'll just create a new function called expand sieve that will be called whenever we need to make our sieve larger. We'll also need to know how much bigger are we going to make our sieve when we expand it. And there's kind of a trade-off here. If you make it too small, like if in my previous example, if we expanded it one at a time, well, we would have to call expand 10,000 times to get from a sieve of size 10,000 to a size of 20,000. And so that's not ideal. But we also don't want to expand by too much. If we make our expansion size 1 million, then we're potentially wasting a lot of memory. And so thinking about sort of the fundamental block of memory management or unit of memory management on many modern operating systems, we might decide to use a block size of 4K. That is 4,096 bytes. And so without going into too much detail, often under the hood, that's the size that many operating systems are use when dealing with memory and memory organization. And so that's a reasonable value to use. If you wanted to actually determine whether that was good, you would have to do more performance testing and tuning to find what the best value might be. But just as a first guess, I think that's a very reasonable starting point. So we'll say expand size equals, now what is this? What have I done here? So 4096 is 2 to the 12th power. But you'll see that this is equivalent to 2 to the 15th power. And that's because we're able to store most likely 8 values per byte. And so that actually is 2 to the 12th times 2 to the 3rd gives us 2 to the 15th. So that's going to be the size of our expansion. Okay, so now let's go in here, and what we want to do is say, if primes is empty, then we're going to expand Sieve. Yeah. But this if statement is not actually sufficient. We want to say while primes dot size is less than or equal to n, then expand Sieve. So we might have to expand our Sieve multiple times in order to reach a size that is adequate. And we'll need to do similarly here, while composite dot size is less than or equal to n, then expand Sieve. All right. So let's write our expand Sieve function now. So we'll say primes expand Sieve, and we'll say old size equals composite dot size, and then we'll say composite dot resize, and we want the new size to be old size plus expand size, and then calc primes. Now, the problem with this, you may have caught it immediately, is that this will recalculate all the same primes we've already calculated, which is not only inefficient in terms of CPU time, but also then will duplicate all those primes that we've already calculated. And so we really want to not recalculate all the primes. We want to calculate the primes greater than some particular value, and that's going to be old size. Now, calc primes doesn't currently take an argument like that, so we'll have to update our code to match. So we'll say calc primes now takes an argument of start, which is the starting point of our search for primes. Now, while we're here, we might as well remove sieve size is no longer needed. Also, we do not need to initialize our sieve to a particular size. We can just start off with an empty sieve, and it will grow as necessary. Okay, so now to update our calc primes function. All right, so if we go down here and we say instead of I equals 0, we'll say I equals start. You may notice that we will only need to actually set these if start is equal to true, but it turns out that often checking some if statement to save just a few cycles to avoid these, it's probably not worth it. So we can just leave that in. That's fine. We don't have to specifically check that start is 0. Okay, so you might still notice that this is missing one important piece of logic, and that is that now we're only finding new primes after a certain point. But when we initialized that section of the sieve, it had all false values, and we need to take the primes we've already found and mark the multiples of those primes in the new section of sieve that we just created. And so let's copy this code, which essentially does the same thing, and we'll do that up here. Actually, no. Let's take advantage of a fun bit of C++ syntax. We'll say uint32t p primes, like so. So this will probably be familiar with to some of you who have used other languages like Java. This is the for each loop. So we're going to loop over all the primes that we found so far and mark the multiples of those primes. Yeah, so now I think we can grab this code here and stick that in there and replace I with P. So this is getting better. But it still has the problem that we're now remarking parts of the sieve that we already marked. And so we don't want to start at P plus P. We really want to start at the smallest multiple of P that is greater than or equal to start. Now the computation to figure that out is a little bit tricky, so let's break that out into its own function. So we'll just say multiple GTE start P. So this function doesn't exist. I just invented it. But we're going to say that that's that this finds the smallest multiple of P that is greater than or equal to start. So that's what this GTE is, just greater than or equal to. And so let's add that to our class. If we just say uint32t multiple GTE, we'll have n and divisor. So this function is a little bit out of place in our primes class. It's not really specific to working with prime numbers. And you could imagine that at some point in the future, we might have a utilities class or something like that that has miscellaneous useful functions in it. And maybe at that point, we would move this in there. But for now, we'll just let it live in our primes class. And so, like I said, the calculation for this is a little bit tricky. And I think even after I explain it, you may have to pause the video and go over some examples with pencil and paper to really understand why this works out, but I'll see if I can explain it. So there's a something called the division algorithm, which is it's really more of a theorem than an algorithm, but it states that any integer n can be written as given some integer n and divisor, you can write n as k times divisor plus r, where r is less than divisor. And in particular, that's going to be the remainder of n divided by divisor, like that. And so we can, just doing a little bit of algebra here, we can move this over to the other side of our equation. And we see that doing n minus n mod divisor gives us a multiple of divisor. And you'll recall that's what we're looking for, is a multiple of divisor. Unfortunately, this gives us the wrong multiple. This gives us the less than or equal to multiple rather than the greater than or equal to multiple. Now, it turns out that there's a little trick that we can use to transform our less than or equal to or multiple LTE function into our multiple GTE. So let's just label this real quick. Multiple LTE would be this, but that's not what we're looking for. We're looking for multiple GTE. And the trick is to find the greatest number that could be the return value from our function and use that as the value for n. And that's the part that I think you're really just going to have to think through that on your own, why that works. I haven't found a great way of explaining that. But so we'll say uint32t is going to be, we'll call this upper, is going to be n plus divisor minus 1. And so the reason that this is the largest value we could potentially return from this function is that if suppose it were 1 larger, n plus divisor, then that means that n plus divisor is a multiple of divisor, which means that n itself would also have to be a multiple of divisor. But then that would be our return value instead. Or if you imagine if it was n plus divisor plus 1, and that was a multiple of divisor, well, similarly, n plus 1 would be a multiple of divisor. And so we can see that n plus divisor minus 1 is going to be the largest value we might return from this function. And it turns out that if we take this value and plug that into our multiple LTE here, that gives us what we want. So then we just say return upper minus upper mod divisor, and that's going to be our multiple GTE function. So that's probably not obvious why that works. We could work through an example. Say we have n is 9 and divisor is 4. Then we would have as the largest, our value for upper here is going to be 9 plus 4 minus 1 is 12. And then 12 mod 4 is 0. 12 minus 0 is 12. And you can see that 12 is indeed the smallest multiple of 4 greater than 9. And so that is the correct value. Okay, so unless I've missed something, I believe that is all we need. So let's see what happens. Oh, I see. I've haven't actually declared this correctly. All right. And we have success. So now we have our primes class will grow automatically as needed and fulfill all our prime testing and calculating needs. So thank you so much for sticking with me through these 4 videos. I really enjoyed making them, and I hope you'll check out the next video, which should be the solution to problem number 10 using our new primes class.